Carbon is an essential element of all organic compounds. Carbon, which is tetravalent, has the ability to successively bond with other carbon atoms to form long chains or rings. The property of self-linkage of carbon atoms is known as catenation. Carbon also forms covalent bonds with hydrogen, oxygen, nitrogen, sulfur, and halogens. These carbon compounds are known as organic compounds. And the branch of chemistry that studies the formation and properties of organic compounds is known as organic chemistry. Organic compounds form the basis of life. For example, deoxyribonucleic acid or DNA is made up of sugar-like 2-deoxyribose and nitrogenous bases. In blood, muscles, and skin. Organic chemicals are also present in clothing, as in nylon fabric. In fuels, as a mixture of C7 to C9 hydrocarbons. In polymers, like polyethylene. In dyes, such as bromophenol blue. And in medicines, such as aspirin. In 1780, chemists discovered that organic compounds can be obtained directly or indirectly from plants and animals. While inorganic compounds are obtained from non-living resources such as minerals and rocks. In 1815, Berzelius, a Swedish chemist, suggested a theory which is known as the vital force theory. In his theory, he stated that organic compounds are produced only under the influence of some mysterious force existing in the living organisms. However, in 1828, Friedrich Wöhler, a German chemist, rejected the vital force theory. Wöhler synthesized an organic compound, urea, by heating an inorganic compound, ammonium cyanate. Later in 1845, Kolb synthesized acetic acid from purely inorganic compound. And in 1856, Berthelot synthesized methane from an inorganic compound. Thus, this led to the end of the vital force theory. A few years later, scientists found out that natural and synthetic organic compounds essentially contain carbon and hydrogen. And at times, they also contain other elements such as oxygen, nitrogen, sulfur, halogens, and phosphorus. Organic compounds made of only hydrogen and carbon atoms are known as hydrocarbons. All other organic compounds are considered to be derived from hydrocarbons by replacing one or more hydrogen atoms with atoms of other elements. Thus, organic chemistry is defined as the chemistry of hydrocarbons and their derivatives. The tetravalence of carbon can be explained from its valence shell electronic configuration. We know that the outermost shell of an atom is known as the valence shell. Electrons present in the valence shell, that is, valence electrons, take part in the chemical reaction. The electronic configuration of carbon is 1s2, 2s2, 2px1 and 2py1. This means that the valence shell has only 4 electrons. All elements tend to complete octet in their valence shell to become stable. Since carbon has 4 electrons in its valence shell, to complete its octet, the valence electrons of it form 4 covalent bonds with atoms of other elements. This characteristic of carbon atom, by virtue of which it forms 4 covalent bonds, is called as tetravalence of carbon. Thus, carbon forms a wide range of compounds. In this example, methane is formed by sharing 4 electrons of carbon with 4 hydrogen atoms. The formation of molecules and their shapes can be explained by considering the hybridization of s and p orbitals respectively. Now, let's look at how hybridization explains the shape of ethene molecule, that is, C2H4. In ethene, each carbon atom undergoes sp2 hybridization. 2 sp2 hybrid orbitals of each carbon atom overlaps with each of the 1s orbitals of 2 hydrogen atoms to form 2 sigma bonds respectively. The remaining sp2 hybrid orbital of a carbon atom overlaps coaxially with a similar sp2 hybrid orbital of the other carbon atom to form a strong carbon-carbon sigma bond by sp2-sp2 overlap. The unhybridized or pure 2pz orbitals of both the carbon atoms overlap laterally to form a weak carbon-carbon pi bond by pp overlap. Pi bond doesn't account for the shape of the molecule. All the 6 atoms forming the sigma bonds lie in one plane, and the pi bond lies perpendicular to the plane. Thus, the shape of the molecule is trigonal planar. Hybridization influences bond length and bond strength in organic compounds, which means that these parameters do influence the shapes of molecules. Among sp3, sp2 and sp, in an sp hybrid orbital, the s character is maximum, that is, 50%. Greater is the s character, closer is the orbital to the nucleus, and hence higher is the electronegativity of that carbon. Also, these effects result in shorter hybrid orbital, shorter bond length and greater bond strength of the bonds formed by sp hybrid orbital. In sp2 hybrid orbital, the s character is 33.3%, and in sp3 hybrid orbital, the s character is only 25%. Hence, the bond length is more in case of the bonds formed by sp3 than sp2 hybrid orbitals, and least in case of the bonds formed by sp hybrid orbitals. In sp2 hybrid orbitals, the s character lies between sp3 and sp hybrid orbitals. Hence, its bond strength and bond length is intermediate between them. Let's compare the CH bond lengths and the bond strengths in ethane, ethylene, and acetylene. Thus, bond strength of sp hybrid orbital is greater than sp2 followed by sp3 as shown here. And the bond length of sp3 hybrid orbital is greater than sp2 followed by sp as shown here. Thus, the greater the s character, the greater is the electronegativity. Sp is more electronegative, followed by sp2 and sp3. Now, let's look at certain characteristic features of a pi bond. The bonds formed by lateral overlapping of pure p orbitals are known as pi bonds. Let's look at the pi bonds in ethylene. Here, the pure p orbitals of both the carbon atoms, which are mutually parallel to each other, form a pi bond that is perpendicular to the plane of the molecule. Rotation of C around the double bond is strongly restricted, as the pi bonds prevent the free rotation around the carbon-carbon bond. In a pi bond, the electron charge cloud is present above and below the plane of the bonding atoms. Hence, these electrons are more exposed and susceptible to attack by electron-seeking reagents. In general, pi bonds provide the most reactive centers in unsaturated molecules. The pi electrons are more tightly held by the carbon atoms in acetylene, as the carbon atoms are sp hybridized compared to the pi electrons of ethylene, in which the carbon atoms are sp2 hybridized. Hence, acetylene is less reactive than ethylene. A chemical formula which represents the arrangement of atoms in a molecule is called the structural formula of a molecule. The various structures of organic compounds can be represented by 4 different ways. They are Lewis structural formula or dot structural formula, dashed structural formula, condensed structural formula, and bond line structural formula. Let's first look at the Lewis structural formula. The Lewis structure is named after the scientist Gilbert N. Lewis. In Lewis dot structure, a pair of electrons forming a covalent bond is represented by using a dot or cross. However, the Lewis dot structure can be further simplified by representing a pair of electrons by a dash. This simplified representation is called dash structure. Thus, a pair of electrons forming a single covalent bond is represented by a dash. A double covalent bond is represented by a double dash, and a triple covalent bond is represented by triple dash. Organic compounds containing heteroatoms with lone pair of electrons are represented by a pair of dots on the respective heteroatom. This structure represents the bonding between atoms in a molecule and also shows the presence of lone pairs present on the atoms, if any. This structural formula shows the arrangement of atoms and the type of bonds present between the atoms in the molecule. Here's the dash structural formula for ethane. In ethane, 2 atoms of carbon are attached to each other by a single covalent bond, and all carbon-hydrogen bonds are also single covalent bonds. In ethane, 2 atoms of carbon are connected with a double bond, and 2 hydrogen atoms are attached to each carbon by a single bond. In ethyne, 2 atoms of carbon are connected with a triple bond, and 1 hydrogen atom is attached to each carbon by a single bond. In methanol, carbon is attached to 3 hydrogen atoms and 1 hydroxyl group. 2 lone pairs of electrons present on the oxygen atom of hydroxyl group are represented as shown here. Now, let's look at the condensed structural formula. In a condensed structural formula, some or all the dashes that represent covalent bonds are omitted, and the number of identical groups attached to a carbon atom is represented by a subscript. Thus, a condensed structural formula is an abbreviated form of dash structure. The condensed formula of ethene, ethine, and methanol are represented as shown here. At times, the formula is further condensed by enclosing the repetitive structural unit within a bracket and placing an integer as a subscript, indicating the number of times the structural unit is repeated. In this case, CH2 is put within brackets and has a subscript of 6, indicating that the structural unit CH2 repeats 6 times. Finally, let's look at the bond line structural formula. A bond line structural formula is a short and simplified method for representing an organic compound. In this method, carbon-to-carbon bond is represented by lines drawn in zigzag fashion, represent carbon-to-carbon bonds, and line terminals generally represent methyl groups if they don't have a functional group, whereas the line junctions represent the carbon atoms attached to appropriate number of hydrogen atoms required to satisfy the valency of carbon. If any heteroatoms are present in place of hydrogens, they are specifically written by using their symbols as shown here. Let's consider the dash structural formula of 3-methyl-octane. Now, let us represent the bond line structural formula for this as shown here. Here is the condensed structural formula and the bond line structure formula for 2-bromobutane. Cyclic compounds are represented by polygons. In a polygon, the corners represent a carbon atom and the sides represent a carbon-carbon bond. Symbol of atoms other than carbon and hydrogen are shown on the structure. Organic molecules can be represented by using the solid and dashed wedge formula. This is a three-dimensional structural representation of an organic compound. This formula can be represented on the paper by using 3 conventions, that is, a dash, a solid wedge, and a dashed wedge. A dash is used to mean that the bond is in the plane of the paper. A solid wedge means that the bond is projecting out of the paper and is towards the observer. A dashed wedge is used to mean that the bond is projecting out of the paper and is away from the observer. The 3D image for the methane is shown here. 3-dimensional molecular models are used for better visualization and perception of the shapes of organic compounds. There are 3 types of molecular models: framework model, ball and stick model, and space filling model. In the framework model, the atoms are not shown. Only the bonds connecting the atoms of a molecule are shown. This model is used to study the patterns of bonds and does not consider the size of the atoms. In the ball and stick model, both bonds and atoms are shown. The balls represent atoms while sticks represent bonds. Compounds containing double bond, as in ethene, are represented in a different way. In place of a stick, a spring is used to represent the double bond. Hence, this type of model is called ball and spring model. Another type of molecular model is space-filling model. The relative size of each atom is based on van der Waals radius. That is, the volume occupied by each atom is shown. Bonds are not shown in this model. To simplify and systematize the study of organic compounds, they can be classified on the basis of their structure as open chain or acyclic compounds and closed chain or cyclic or ring compounds. Open chain compounds are also known as aliphatic compounds. The term aliphatic is derived from Greek word alipha, meaning fat or oil. The compounds in this class are derived from vegetable or animal fats. Open chain or acyclic compounds are compounds in which carbon atoms are linked by straight or branched chains. Some examples of straight chain compounds include butene, butyne, pentyl alcohol, acetone. Some examples of branched chain compounds are isobutane, isobutylene. In a cyclic or ring or closed chain compound, the carbon atom and any other atom, if any, are joined together to form a closed ring. For example, in cyclohexane, 6 carbon atoms join together and form a closed ring. Cyclic compounds can be further classified as homocyclic or carbocyclic compounds and heterocyclic compounds. The word homo means same. Thus, homocyclic or carbocyclic compounds are those in which the ring consists of only carbon atoms. For example, in cyclohexane, the ring consists of only carbon atoms. The word hetero means different. Heterocyclic compounds are those in which the ring consists of carbon atoms. As well, the other atoms like sulfur, oxygen, or nitrogen. Homocyclic compounds can be further classified as alicyclic compounds and aromatic compounds on the basis of their characteristic properties. Homocyclic compounds, which resemble aliphatic compounds in their properties, are called alicyclic compounds or aliphatic cyclic compounds. An alicyclic compound consists of a ring which has only carbon atoms. For example, cyclopropane, cyclobutane, and cyclohexane. Aromatic compounds are benzene and the compounds that resemble benzene in their behavior. Aromatic compounds can be further classified as benzenoid compounds and non-benzenoid compounds on the basis of the presence or absence of benzene ring. Aromatic compounds containing isolated or one or more fused benzene rings and their functional derivatives are known as benzenoid aromatic compounds. Benzene is the parent compound in benzenoid derivatives. A non-benzenoid compound is one that does not contain a benzene ring. For example, tropolone as shown here. There is another class of aromatic compounds called heterocyclic aromatic compounds. These compounds contain heteroatoms such as nitrogen or sulfur or oxygen in addition to carbon atoms in the ring and resemble benzene in their properties. For example, pyridine, thiophene and furan are heterocyclic compounds containing heteroatoms, sulfur and oxygen respectively. The other way to classify the organic compounds is on the basis of functional groups. A functional group is an atom or a group of atoms present in a molecule, which determine its characteristic properties. For example, hydroxyl group and carboxylic acid group is the functional group of alcohols and carboxylic acids respectively. Organic compounds can also be classified on the basis of homologous series. The successive members or series of organic compounds with a characteristic functional group having the same general molecular formulae and differ by CH2 unit form a homologous series. The successive members of a homologous series are called homologs. For example, the homologous series of alkanes are methane, ethane, propane, butane, and so on. The successive members such as methane and ethane are called homologs. There are millions of compounds that fall under the branch of organic chemistry. To easily identify these compounds and their structure, scientists have assigned names to these compounds. The system of assigning a name to a compound is known as nomenclature. There are two systems for naming organic compounds: the common or trivial system and the IUPAC system. Let's look at the trivial system. The trivial names are given on the basis of the source and certain properties of organic compounds. For example, citric acid is named so as it is found in citrus fruits. Formic acid is named so as it is obtained from the destructive distillation of formica, which means red ants in Latin. This system was commonly used before 1892, and it did not follow any standardized rules. Moreover, more than one common name is given for certain compounds. To remember the common names given at random for large number of compounds that are discovered day to day is difficult. Hence, the need to develop a systematized method for naming organic compounds is found to be indispensable. Thus, in 1947, the IUPAC, that is the International Union of Pure and Applied Chemistry system of naming compounds, was first developed. The IUPAC system of nomenclature is a set of logical rules devised and used by chemists in which the name of a compound correlates to its molecular structure, thus making it intuitive for a person to deduce the structure from the name. However, common names are preferred for the IUPAC names, which are lengthy or complicated. Let's understand how IUPAC names are assigned to various compounds. The IUPAC name of an organic compound basically consists of three parts: the root word, the suffix, and the prefix. A root word indicates the length of the continuous selected carbon chain. A chain which consists of up to 4 carbon atoms is assigned special word roots based on the common names of alkanes. Thus, the word root for 1 carbon atom is meth, 2 carbon atoms is eth, 3 carbon atoms is prop, and 4 carbon atoms is but. A chain that consists of more than 4 carbon atoms is assigned a root word derived from the names of Greek numerals. Thus, the root word for 5 carbon atoms is pent, 6 carbon atoms is hex, 7 carbon atoms is hept, 8 carbon atoms is oct, 9 carbon atoms is non, and 10 carbon atoms is dec. Now let's look at the suffix. There are 2 types of suffixes: primary and secondary suffix. A primary suffix indicates the nature of the carbon chain that is saturated or unsaturated, and the secondary suffix indicates the functional group present in the compound. A primary suffix is added to the end of the root word. It indicates if a compound is saturated or unsaturated. That is, whether the compound consists of a single or multiple bonds. The 3 primary suffixes are ane for alkane, ene for alkene, and ine for alkyne. A secondary suffix indicates the nature of the functional group present in a compound. Thus, the 3 components can be combined to form part of the compound name. For example, the root word eth, primary suffix ane, and secondary suffix all together form the IUPAC name ethanol. A root word eth, primary suffix ane, and secondary suffix oic acid together forms the IUPAC name ethanoic acid. If a functional group is present, then E of the primary suffix is replaced by the secondary suffix. Now let's look at the final component, the prefix. There are 2 types of prefixes: primary prefix and secondary prefix. A primary prefix is used to differentiate acyclic and cyclic compounds. However, the rules for using these are slightly different. For example, in cyclic compounds, the prefix cyclo is added before the root word. In the IUPAC system, some groups are not considered as functional groups. They are treated as substituent groups. In such cases, the substituent acts as the secondary prefix. Some secondary prefixes and their substituent groups are fluoro for fluorine, chloro for chlorine, bromo for bromine, iodo for iodine respectively. However, in acyclic compounds, the primary prefix is not used. So, if the prefix cyclo is not used, it indicates that the compound is acyclic, as in propane. We know that hydrocarbons are organic compounds that contain only carbon and hydrogen. The hydrocarbons, which consist of carbon-carbon single bonds, are said to be saturated and are called alkanes. The general formula for alkanes is CnH2n plus 2, where N indicates the number of carbon atoms. We know that there are two systems for naming organic compounds, the common or trivial system and the IUPAC system. The names of the first four members of alkanes are based on the trivial names. They are methane, ethane, propane and butane. The IUPAC name of an alkane basically consists of two parts, the root word and the suffix. A root word indicates the length of the continuous selected carbon chain. A chain which consists of up to 4 carbon atoms is assigned special root words from their trivial names. Thus, the root word for 1 carbon atom is meth, 2 carbon atoms is eth, 3 carbon atoms is prop, and 4 carbon atoms is but. A chain that consists of more than 4 carbon atoms is assigned a root word derived from the names of Greek numerals. Thus, the word root for 5 carbon atoms is pent, 6 carbon atoms is hex, 7 carbon atoms is hept, 8 carbon atoms is oct, 9 carbon atoms is non, and 10 carbon atoms is dec. A suffix indicates the nature of the carbon chain. As the carbon chain is saturated, suffix ane is used. For example, a compound that has 2 carbon atoms in the chain will have the root word eth and the suffix ane. Thus, its IUPAC name will be ethane. Similarly, the IUPAC name of an alkane having 4 carbon atoms is thus but plus ane, butane. Alkanes can be straight chain alkanes or branched chain alkanes. Let's look at the IUPAC names of certain straight chain homologs of alkane series. The IUPAC name of an alkane having 1 carbon atom is methane. The IUPAC name of an alkane having 2 carbon atoms is ethane. The IUPAC name of an alkane having 3 carbon atoms is propane. The IUPAC name of an alkane having 4 carbon atoms is butane. The IUPAC name of an alkane having 5 carbon atoms is pentane, and so on, as shown here. Let's look at the trivial and IUPAC names of the branched chain alkanes. Small chains of carbon atoms attached at 1 or more carbon atoms of the parent chain is said to be a branched chain. These small chains of carbon atoms are called alkyl groups. Let us briefly study about the alkyl groups. The group which consists of 1 hydrogen atom less than an alkane is called an alkyl group. For example, if 1 hydrogen atom is removed from methane, that is CH4, we get the alkyl group CH3. An alkyl group is named by replacing the ane in the name with YL. Thus, the name of alkyl group of methane will be methyl. At times, abbreviations are used for certain alkyl groups. For example, methyl is abbreviated as Me, ethyl is abbreviated as Et, propyl is abbreviated as Pr, and butyl is abbreviated as But. Alkyl groups are called as primary, secondary, or tertiary based on whether 1, 2, or 3 other carbon atoms are directly attached to the carbon atom in the chain. Alkyl groups derived from the saturated hydrocarbons having minimum 3 or more carbon atoms can have the following possible branched structures. For example, propyl and butyl groups can have the following structures. The trivial names given for these structures are isopropyl, secondary butyl, and tertiary butyl, as the carbon atom is attached to other 2 and 3 carbon atoms respectively. Now let us see how in the trivial system, the various straight chain and branched chain alkanes, such as butane and pentane, are differentiated. If all the carbon atoms form a continuous straight chain, that is, without branching, then the prefix N is given to the name of the alkane. For example, for the structure shown here, which consists of a continuous chain of 5 carbon atoms, the name given is N-pentane. If the carbon atom next to the terminal carbon having a methyl group as a branch is attached to a continuous carbon chain, then a prefix iso is given to the name of the alkane. For example, for the structure shown here, which consists of a branched chain and is a 5-carbon system, the name given is isopentane. If the carbon atom next to terminal carbon has 2 methyl groups as branches, is attached to a continuous carbon chain, and then a prefix neo is given to the name of alkane. For example, for the structure shown here, which consists of 2 branched chains and is a 5-carbon system, the name given is neopentane. The corresponding alkyl groups are named as N-alkyl, isoalkyl, neoalkyl respectively. Examples of N-alkyl, isoalkyl, and neoalkyl are shown here. They are N-pentyl, isopentyl, and neopentyl respectively. Now let us look at the IUPAC rules to name the branched chain alkanes. Rule 1. Select the longest carbon chain in the molecule. In this compound, the longest chain consists of 9 carbon atoms. Hence, it is also called as parent chain or root chain. Selecting the longest chain as in second case is not correct because the parent chain consists of only 8 carbon atoms. Rule 2. Number the parent chain that has branches. The numbering of the chain is done in such a way that the branched carbon atoms get the lowest possible number. If we number the chain from left to right, then the branches are located at carbon 2 and 6. And if we number the chain from right to left, then the branches are located at carbon 4 and 8. As per the rule 2, the numbering should be done from left to right. Rule 3. Name the branched chain alkane. The name of the alkyl group attached to the carbon atom as a branch, that is, a substituent is given the appropriate prefix to the name of the parent alkane, and the position of the alkyl group on the parent chain is indicated by writing the appropriate number. If more than one alkyl substituent is present, then the names of alkyl groups are listed in alphabetical order. For example, in this compound, the alkyl groups methyl and ethyl are fixed to the alkane nonane in the alphabetical order, and positions of the substituents are 2 and 6. Hence, the name of the compound is 6-ethyl 2-methyl nonane. The numbers are separated from the alkyl group name by using a hyphen. Rule 4. Name the identical alkyl groups at different positions of the carbon chain using the prefixes di, tri, tetra, etc. If more than one identical alkyl group is present on the parent carbon chain, at different positions, prefixes such as di for 2 identical alkyl groups, tri for 3 identical alkyl groups, tetra for 4 identical alkyl groups, etc., are used with the alkyl group. For example, while naming the following compound that has 2 methyl substituents at 2 and 4 positions, the prefix di is used. Hence, the name of the compound is 2,4-dimethyl-pentane. Similarly, prefix tri is used while naming the following compound. Hence, the name of this compound is 2,2,4-trimethyl-pentane. The position numbers of the substituents are separated by comma. Note that the prefixes di, tri, etc. are not considered when deciding the alphabetical order of the alkyl groups. In the following compound, the ethyl group name is written first as per alphabetical order, ignoring the prefix di used for methyl group. Rule 5. Numbering different alkyl groups at equivalent positions. If 2 substituents are present on equivalent positions, then the lower number is assigned to the group that appears first in the alphabetical listing. For example, in case 1, the ethyl group is present on carbon 3, which is assigned a lower number than its position at 6 in case 2. Hence, the correct name for the compound would be 3-ethyl 6-methyl octane. Rule number 6. Numbering the complex substituent. If the substituent, that is, the alkyl branch on the parent chain, is complex, then the carbon atom of the branch attached to the parent chain is given the position 1 while numbering as shown. The name of this alkyl branch is placed in the parenthesis while naming the compound. The use of prefixes such as iso, secondary, tertiary for naming the substituents, that is the alkyl groups, is allowed in the IUPAC nomenclature, but such alkyl groups should not be further substituted. Iso and neo are considered, but secondary and tertiary are not considered to be part of the fundamental name of alkyl groups during writing the names in an alphabetical order. The parent chain, which contains more number of side chains, is selected. The chain highlighted in red has 3 side chains attached to it. If we select the other chain, as shown as the parent chain, it will have only 2 side chains attached. Hence, case 1 is the correct way to select the chain. The chain should be numbered from the end which is closer to the alkyl groups. Here, the alkyl groups are attached to carbon 3 and 5. Here, the substituents are attached to carbon 6 and 8. So, it is far from the substituent. Hence, it is a wrong way of numbering. Then, the substituent groups are numbered. As there are 4 carbon atoms present, the alkyl group is butyl. The ethyl group is attached to the second carbon atom. Hence, the name of the substituent is 2-ethyl-butyl. The substituent 2-ethyl-butyl is attached to the 5th carbon atom of the parent chain. Hence, it is 5-2-ethyl-butyl. Here, 2-ethyl-butyl is written in parentheses. The parent chain consists of 10 carbon atoms. Hence, it is decane. 2 methyl groups are attached to the 3rd carbon atom. Hence, their name will be 3,3-dimethyl. The name of the compound will be 5-2-ethyl-butyl 3,3-dimethyl decane. Now let's look at the nomenclature for the cyclic compounds, also known as cycloalkanes. Cycloalkanes are saturated compounds containing a ring of carbon atoms. They are named by adding the prefix cyclo to the corresponding straight chain alkane. For example, in a ring consisting of 5 carbon atoms, the prefix cyclo is added to pentane. Hence, the name of the compound is cyclopentane. If different alkyl groups are present in a cyclic compound, then the names are written in alphabetical order. For example, in the following compound, as per the alphabetical order, methyl group comes first, followed by propyl. Hence, the name of the compound is 1-methyl-3-propyl cyclohexane. This cyclic compound consists of 6 carbon atoms in a ring. Hence, it is cyclohexane. The compound is numbered from right to left. The ethyl group is attached to the 3rd position of the cyclohexane, and 2 methyl groups are attached at position 1. Hence, the name of the compound would be 3-ethyl-1,1-dimethyl cyclohexane. If the compound is numbered from left to right, then 2 methyl groups are attached at 3rd position. This means that the mode branching is at the 3rd carbon atom, and the name of the compound would be 1-ethyl-3,3-dimethyl cyclohexane. This is incorrect. We've learned that a functional group is an atom or a group of atoms present in a molecule, which determines the characteristic properties of the molecule. For example, methanol, ethanol, and propanol all contain the hydroxyl functional group. All these compounds react with sodium metal and liberate hydrogen. Thus, we can conclude that organic compounds that have similar functional groups show similar chemical reactions. Functional groups play an important role in determining the properties of a compound and are used to organize organic compounds in different classes. Based on the structure of the compounds, they have been organized into classes and assigned IUPAC group prefix and suffix. The alkane group suffix is ane, A-N-E. The alkene group suffix is ene. The alkyne group suffix is ine. The halide group prefix is halo. The alcohol group prefix is hydroxy and the group suffix is -ol. The aldehyde group prefix is formyl or oxo and the group suffix is -al. The ketone group prefix is oxo and the group suffix is -one. The nitrile group prefix is cyano and the suffix is nitrile. The ether group prefix is alkoxy. The carboxylic acid group prefix is carboxy and the suffix is oic acid. The carboxylate ion group suffix is -ate. The ester group prefix is alkoxycarbonyl and the suffix is -ate. The acyl halide group prefix is halocarbonyl and the suffix is oil halide. The amine group prefix is amino and the suffix is amine. The amide group prefix is carbamoyl and the suffix is amide. And the nitro group prefix is nitro. The sulfonic acid's prefix is sulfo and the group suffix is sulfonic acid. Now let's see how we can use the prefix and suffix to assign names to compounds. Step 1. Identify the functional group in the compound. In this example, the functional group OH belongs to the class alcohol. As per the IUPAC system, the suffix for the alcohol group is OL. Step 2. Number the longest chain. If we number the chain from right to left, then the OH group is on second position. And if we number the carbon chain from left to right, then the OH group is on fourth position. As per the naming convention, functional group should be attached to the carbon atom with the lowest possible number. Hence, case 1 is the correct way of numbering. Step 3. Assign a root word. As there are 5 carbon atoms in the chain, the root word will be pent. Step 4. Assign a primary suffix. The chain only contains single bonds. Hence, the primary suffix will be ane. Step 5. Assign a secondary suffix. The functional group is OH, that is alcohol. Hence, the secondary suffix will be ol, OL. Step 6. Specify the position of the functional group. The functional group OH is present at the second position. Hence, the position of the functional group will be 2. Thus, the name of the compound is pentan-2-ol. But some compounds have more than one functional group. These are known as polyfunctional compounds. In such compounds, one of the functional groups is chosen as the principal functional group. The principal functional group is selected based on the order of decreasing priority as shown here. Carboxylic acid has the highest priority, followed by sulfonic acid. Esters, alkyl halides, amides, nitriles, aldehydes, ketones, alcohols, amines, alkenes, and alkynes. In the given compound, carboxylic acid will be the principal functional group, as it has higher priority than the ketone functional group. The name of the compound is written on the basis of the principal functional group. For this, we need to start numbering the carbon chain from the end nearer to the carbon atom to which the principal functional group is attached. The principal functional group will come as a suffix. For carboxylic acid, the suffix oic acid is used. The other functional groups act as substituents, and they are written by using appropriate prefixes. Here, the substituent is ketone and the prefix used for ketone is oxo. Thus, the name of the compound is 5-oxohexanoic acid. If the same functional group appears more than once in a compound, we name the compound by adding di, tri, etc. before the suffix, and the full name of parent alkane is written before the suffix. In this case, since two carbons are present, therefore the word root is eth. A single bond is present, therefore the prefix is ane. Hence, the name of the compound is ethane 1,2-diol. Now let's name this compound. In this compound, there are two functional groups attached, nitrile group and alcohol group. As the nitrile group has higher priority than alcohol group, we will number the carbon chain such that the carbon of nitrile group gets position 1. Hence, the name of the compound will be 3-hydroxy-4-methyl-pent-4-ene-1-nitrile. The terminal E of the parent chain is retained as it is followed by a consonant and not by a vowel or Y. On the other hand, in the next compound shown here, there is a double bond and a triple bond. In IUPAC nomenclature of organic compounds, a double bond gets preference over a triple bond. Hence, the name of the compound will be pent-3-ine-1-ene. Monosubstituted benzene has only one substituent attached to the benzene ring. While writing the IUPAC name of the monosubstituted benzene, the substituent's name is placed as a prefix to the word benzene. For example, in this compound, the substituent is nitro. Hence, the name of the substituent, which is nitro, is placed as a prefix to the name of the parent compound benzene, and the name of the compound becomes nitrobenzene. Similarly, if the substituent is bromine, then the name of the compound is bromobenzene. Now let us name the following monosubstituted benzenes having the substituents methyl, methoxy, amino, and hydroxy respectively. The names of these compounds are methylbenzene, methoxybenzene, aminobenzene, and hydroxybenzene. The common names for these compounds are also widely in use. The common names for these compounds are toluene, anisole, aniline, and phenol respectively. Now let us discuss the nomenclature of the benzene that has more than one substituent. If more than one substituent is present, then the positions of the substituents are indicated by numbering the carbon atoms of the ring. The numbering is done in such a way that the sum of the locants is the least. This means that the substituents should be located at the lowest numbers possible. Let us understand this by considering the following two cases. In case 1, the carbon atoms are numbered in the clockwise direction. As a result, the two bromine atoms are present at the positions 1 and 3. In case 2, the numbering of carbon atom is done in the anti-clockwise direction. As a result, the two bromine atoms are present at the positions 1 and 5. According to the rule, case 1 follows the correct way of numbering. 3 isomers are possible for a disubstituted benzene. These 3 isomers are differentiated in the trivial system by using the names ortho, para, and meta, which are abbreviated as O, P, and M respectively. The positions of the substituents in a disubstituted benzene is thus indicated by using the appropriate prefix ortho, meta, or para. When the substituents are present on the adjacent positions of the benzene ring, that is, on the first and second positions, then in the IUPAC system of nomenclature, the positions of these substituents are indicated as 1, 2, and in trivial system, the prefix ortho is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 2 positions. Hence, the name of the compound is 1,2-dibromobenzene or ortho-dibromobenzene. When the substituents are present at the alternate position of the benzene ring, that is, on the first and third positions, then, in the IUPAC system, the positions of these substituents are indicated as 1, 3, and in the trivial system, the prefix meta is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 3 positions. Hence, the name of the compound is 1,3-dibromobenzene or meta-dibromobenzene. When the substituents are present on diagonally opposite positions of the benzene ring, that is, at 1 and 4 positions, then, in the IUPAC system, the position of these substituents are indicated as 1, 4, and in the trivial system, the prefix para is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 4 positions. Hence, the name of the compound is 1,4-dibromobenzene or para-dibromobenzene. Similarly, the names of the following compounds with 2 different substituents on the benzene ring are 2-ethyl-anisole or ortho-ethyl-anisole and 4-nitroaniline or para-nitroaniline respectively. Now let's look at the nomenclature of tri or higher substituted benzene. Tri-substituted benzene has 3 substituents attached to the benzene ring. Let's look at the rules for naming such compounds. Trivial system of nomenclature cannot be employed as it has more than 2 substituents. This compound has 3 bromine groups attached to the benzene ring. If more than 2 substituents are present, then the positions of the groups are indicated by numbering the carbon atoms according to the lowest locant rule. This means the sequence in which the numbering is done should have the lowest combination of numbers. If the carbon atoms are numbered in the clockwise direction, then the bromine substituent is found at positions 1, 2, and 4. If the carbon atoms are numbered in the anticlockwise direction, then the bromine substituent is found at positions 1, 4, and 6. Hence, according to the lowest locant rule, the correct way of numbering is followed in case 1. Thus, the name of the compound is 1,2,4-tribromobenzene. In this compound, there are 3 different substituents attached to the benzene ring. According to lowest locant rule, the substituent positions in the ring are identified. Hence, the name of the compound is 1,chloro-2,4-dinitrobenzene and not 4-chloro-1,3-dinitrobenzene. In certain cases, the common name of the benzene derivative is taken as the base compound. Thus, anisole is a base compound in the following structure. The numbering of the carbon atom starts from the carbon bearing substituent of the base compound. Thus, the carbon bearing substituent of the base compound, methoxy, is assigned the number 1. Then, the direction of numbering is chosen in such a way that the next substituent gets the next lowest number. In case 1, the numbering is done in the clockwise direction. Thus, the next substituent gets the position 2. Hence, the positions of the substituents present are 1, 2, and 4. In case 2, the numbering is done in the anticlockwise direction, and the substituents get the positions 1, 4, and 6. As per the lowest locant rule, case 1 is the correct way of numbering. Thus, the name of the compound is 2-chloro-4-methylanisole. Note that the names of the substituents are written in alphabetical order. Thus, chloro comes first, followed by methyl. In this compound, the benzene ring is attached to an alkane with a functional group. In such cases, the benzene ring is considered as a substituent. The name of the benzene ring, when it acts as the substituent, is phenyl. The phenyl group is written as C6H5 or abbreviated as PH. The 2 bromine atoms act as the functional groups. The alkane is numbered as per the lowest number rule. In case 1, the carbon atoms are numbered from left to right. As a result, the substituent and the functional group are assigned the positions 1, 2, and 3. In case 2, the carbon atoms are numbered from right to left. As a result, the substituent and the functional group are assigned the positions 3, 4, and 5. According to the lowest locant rule, case 1 follows the correct way of numbering. Bromine is attached to the second and third carbon atoms, hence should be named as 2,3-dibromo. Phenyl is attached to the first carbon atom, hence should be named as 1-phenyl. The alkane has 5 carbon atoms, hence should be named as pentane. Thus, the name of the compound is 2,3-dibromo-1-phenylpentane. Let's take a compound with the molecular formula C4H10 to understand this concept. If we were to draw the structure of C4H10, we could draw it in the 2 ways shown here. Both the compounds have same number of atoms, that is, 4 carbon atoms and 10 hydrogen atoms. Thus, their molecular formula is the same. The name of the first compound is N-butane and the second compound is isobutane or 2-methylpropane. Both these compounds have different properties. The phenomenon of existence of two or more compounds with the same molecular formula but with different properties is known as isomerism, and the compounds are called isomers. Thus, N-butane and isobutane are isomers. Isomerism can be of two types: structural isomerism and stereoisomerism. The compounds that have the same molecular formula but different structures are known as structural isomers, and the phenomenon is known as structural isomerism. For example, in N-butane and isobutane, the molecular formula is same but their structures are different. Thus, they are structural isomers. Structural isomerism can be of following types: chain isomerism, position isomerism, functional group isomerism, and metamerism. Let's look at chain isomerism. Compounds that have the same molecular formula but different carbon chain, that is, straight or branched chain, are known as chain isomers, and the phenomena is known as chain isomerism. For example, the following three chain isomers are possible with molecular formula C5H12. They are N-pentane, isopentane or 2-methylbutane and neopentane or 2,2-dimethylpropane. Here the carbon skeleton is different in each compound, but the molecular formula is the same. Now, let's look at position isomerism. Compounds that have the same molecular formula, same chain, but which differ in the position of the substituent or functional group are known as position isomers, and the phenomenon is known as position isomerism. For example, the molecular formula C3H8O represents two position isomers. In case 1, the functional group OH is attached to the first carbon atom. Hence, the name of the compound is propan-1-ol. In case 2, the functional group OH is attached to the second carbon atom. Hence, the name of the compound is propan-2-ol. In both the compounds, the molecular formula is same, but the position of the functional group differs. Next, let's look at functional group isomerism. Compounds that have same molecular formula but different functional groups are known as functional isomers, and the phenomena is known as functional isomerism. Propanone and propanal represent two functional isomers having the same molecular formula, C3H6O. Here the functional group differs. That is, in case 1, ketone is the functional group, and in case 2, aldehyde is the functional group. Some examples of functional isomers are alcohols and ethers, cyanides and isocyanides. Finally, let's look at metamerism. Compounds that have the same molecular formula but different alkyl groups attached to the same functional group are called as metamers, and the phenomena is known as metamerism. This type of isomerism occurs due to the difference in the nature of alkyl group attached to the functional group. Metamers always belong to the same homologous series. Let's consider the molecular formula C4H10O. The following isomers can be drawn, that is, methoxypropane and ethoxyethane. Here the alkyl group attached on either side of the functional group is different. In case 1, methyl and propyl are attached to either side of the functional group, and in case 2, ethyl groups are attached to either side of the functional group. Metamers may also be regarded as positional isomers. Some metamers are ethyl aminoethane and methyl aminopropane, 2-pentanone and 3-pentanone. Now let's look at stereoisomerism. In Greek, stereo means space and meros means parts. The isomers which possess the same structural formula but differ in three-dimensional arrangement of atoms or groups in space within the molecule are known as stereoisomerism, and the phenomenon is called stereoisomerism. Stereoisomerism can be of two types: geometrical isomerism and optical isomerism. You'll learn about these stereoisomer types in higher classes.